Yeah.
Thank you. Okay, great. So we're all set. Do you do the intro or do I?
Yeah, I don't know. I mean,
Okay.
I can do the intro. Yeah. Thanks everybody for coming. So this is actually our first Robotics seminar series of this year, this academic year. And I'm really happy that Mark accepted my invitation and going to present. So Mark is a senior lecturer at University of York. His research is into robotics, especially I think Mark had a really kind of diverse interest. He's working on the robots in space, on the ground, and also underwater. So this is a really amazing portfolio that Mark has, and Mark already involved in several European projects where he is the PI at the University of York. And so I think we will actually have a really great talk from Mark. So I will let you take it away.
Thank you very much, Yihong.
Yeah.
So good to see everybody here. My name is Mark Post. I know most of you, I think, by now. So yes, I suppose having a diverse research portfolio is another way of saying that I don't know when to quit. And saying that I'm involved in space, ground and water robotics only means that I'm a real masochist when I choose my targets for the problems to solve. So yes, I mean, my talk today is on networking with dynamic reconfigurability and robustness for modular spacecraft. And I suppose this is kind of the extreme end of the complexity or difficulty spectrum that you might encounter when you're talking about robots communicating with each other. However, I think it's very important. But communications, to start out with, is something that goes hand in hand with intelligence. Humans have evolved because of communication. We can communicate between different individuals without being the same, unlike robots, which often are the same. We can transmit our knowledge over physically long distances, which is an absolute necessity for internet and things like that these days. And we can store knowledge in a consistent format for long periods of time, and in most cases, go back to it and still understand it. This is something we want our artificial systems to do as well. And you may ask, why am I focusing on communications when we have a perfectly good communications group next door who make this their entire focus and who do quite a lot of work in this area, excellent work. I look at it in a slightly different perspective. I see it as an enabler for artificial intelligence and for robotic systems as well, especially in harsh environments where they absolutely have to work together with no human intervention. For this reason, space robots, I believe, really do need internet too. We have internet here on the planet Earth. We can get messages from one side of the globe to the other in milliseconds. It's a wonderful achievement. However, let's say we have robots that are traveling throughout the solar system now. And robots that travel through the solar system have to go very long distances. We now have something called an interplanetary internet that NASA and ESA have to worry about, where you have robots on Earth, Mars, satellites around Jupiter, other places in the solar system. You have extremely long delays, days, weeks, months in some cases. You also have link outages, even close to Earth, where you have communications to the ground. You have clouds going over that will impede optical links, and you have variations in the environment that will impede radio links. You have high bit error rates due to harsh environment, and you also get non-real-time arrival of data because stuff arrives out of order. It's sent from different places at different times in some cases, and it's passed through different routing links. You also have asymmetric channel rates in many cases. A satellite, communication satellite, actually an Earth observation satellite, I should say, sends down lots and lots of data. It only sends up a few bytes every so often. So your downlink is huge and your uplink is tiny. Some of you on internet plans that don't include uplink bandwidth might be familiar with this problem. We need to deal with this somehow in an autonomous and robust fashion. And it's not just internet now. Probably all of you have a local area network at home. You know, IPv4, 192.168.0.1 or some other subnet. We've done long distance links. We can do interplanetary communications with long delays with the protocols I'll be mentioning in this presentation. But now we have the challenge of let's send up modular spacecraft. The new space is the name that they give. It's kind of like Industry 6.0. New space is the idea behind space is easily accessible. It's inexpensive. We can send up modular spacecraft. We can send up space robots. We can put warehouses in space to assemble stuff in space. It's modular systems, and they have to communicate too. And it's a lot more like a local area network, because you're not going to set up a huge interplanetary link for something that's 10 meters away over there on the platform that you're on. We now need to do IoT in space too. And that's the direction we're going. That's kind of the state of the art right now. And you'd be surprised how few people are doing it right now. It's a very, very, talk about local area networks in space. Most people don't really know how it would work, but it's a thing now. It's important. And the reason why it's important is we now have projects like Modular, and my video has decided not to work. So instead, what I'm going to do is I'm going to pull up a video from YouTube that shows exactly the same thing. This is the video I want to show you. Whoops. Here we go. And Modular is a project that I was involved in about the same time I left Strathclyde and played in New York, actually, back in 2017, 2018. And this is what they produced. Imagine this is a spacecraft down here. Imagine that these are components of a spacecraft: batteries, communication systems, power systems, radio systems, processors. We can assemble them on orbit using robot arms, using robotics. We can assemble satellites. We can take satellites, take them apart, take off malfunctioning parts, put on new ones, and you only have to put up the parts that you need to replace, which means you don't have to send up huge bus-sized satellites like NVSat anymore. Send up a platform once, then you have a bunch of small rocket launches to put smaller payloads on. It's so much cheaper. As you know, probably, the cost of getting a kilogram into space is in the hundreds of thousands. So the less mass we send up, the better. And this is the kind of autonomous robotic system that will be reconfiguring these modules. So that was the start of modular spacecraft. We now have a project called StarFab. This is completely new. This started at the beginning of this year. It's currently active. So with a number of partners that you see along the top there, we are building the world's first demonstrator of a modular robot space warehouse. Very exciting stuff. And the idea is that these modules of spacecraft, these pieces, Minecraft blocks in a sense, are going to be stored in a unit that's probably not going to look like this. We've already changed the design, but the basic idea is all your modules are stored in space, and they can be moved around by robots. So you have walking manipulators like this walking around on the outside or the inside of the warehouse and assembling satellites. And you have a satellite that docks here with perhaps with a new cargo of modules, or you have a satellite that needs repair. You offload the old modules, put the new ones on, and relaunch it. All done in orbit by robots. All of these pieces need to communicate. Ideally, they can communicate by wired networks, which is the main focus. We also will need wireless at some point, because sometimes you have free-floating spacecraft, you have free-floating modules. Sometimes you need to communicate with them. So that's the driver of this. That's why it's important. The part York is doing, just for your interest, is mainly focused on the inspection and maintenance part. So we're actually designing an inspection module here. It's got infrared cameras, it's got stereo cameras, it's got a profilometer on it. It will be inspecting all of these modules. So if you get a micrometeoroid damaging it, you get thermal damage, you get some kind of surface damage, you can detect it robotically. Every warehouse has to have its quality control system. So that is what we're developing, using machine vision techniques to actually identify damage on modular systems. So these modules have to connect together somehow. And as you've probably heard the adage, the great thing about standards is that there's so many of them. Well, that's true in space too. These modules need to connect by some kind of standard interface. Otherwise, there's no point in it being modular, right? They all have to talk to each other. Standard interfaces that have been developed include DLR's IBOS, Serum by Center. I was actually involved a bit in this project that developed that. HotDoc by Space Application Services. This is the preferred one for StarFab because Space Application Services is running StarFab. Yeah, it doesn't really help the landscape of modular space systems to have 3 separate standards. So there is now a project called Space USB that is trying to combine all these standards together. You know, that's the way engineering works these days. You develop a bunch of standards and then you have to have a project that merges the standards to produce yet another standard. So cross fingers, knock on wood, we will end up with an actual standard that everybody can agree on after this. That being said, of course, you know what I'm going to say next. Obviously, we've developed our own standard too. So it doesn't help things, yes, but it's good for our research because we've actually solved a few problems as well. And that's a big part of this presentation as well. So how can you interface things in space? Some colleagues of mine at Strathclyde developed a table here. There's mechanical linkage methods, hooks, rotators, clamps. There's electrical methods, pins, tabs, slip rings. And then there's several data protocols that can be used. We have CAN bus. You may be familiar with some of these. CAN bus, SpaceWire, time-triggered Ethernet, FireWire used to run all of your cameras many years ago. You know, MILBus. There are thermal systems that you need to actually transfer thermal energy between modules. It's a thing in space, very important. I want to highlight though, all these are like TRL 7 and 9. Most of these have been tested in space. Wireless TRL 3 to 4. It's barely out of the laboratory. We still haven't done this. We're just starting on this. In fact, that's the key thing. So how do we make a standard interface for these modular systems standard? Well, there's fairly good agreement on the requirements. Mechanical requirements mean there's only one design of connector. It has to be androgynous, has to absorb loads. You need positional tolerance because it's hard to get robot arms to move things precisely, especially if you're docking in space and you don't know exactly what your kinematics are. You need positional tolerance, single-sided disconnect. You have 2 modules, one of them fails. The other one has to disconnect from it. If you can't disconnect with one module from a non-cooperative module, no good. So that's another key thing. You need multiple levels of services. Nobody's going to put every kind of interface, data, fuel, thermal, communications, power on every kind of interconnect. It's too expensive. So some of them have some things, some of them have others. This is an early Serum concept by Center. It changed a little bit after this, but it kind of illustrates the way that people think of space docking connectors. You know, it has to have lots and lots of ways of getting stuff through it. It has to be physically robust, and it has to have single-sided disconnect. It has to be androgynous. You also need electrical protection. You need to have many different contacts for many buses, high data rates, tolerance to space conditions. And again, as I mentioned, you'd actually often need to transfer fluid through these things for refueling and such. So this is the challenge that we have when we try to interface things in space. And once we interface them, we now have modular systems, which means you're not just docking things once. You've got to pull them apart and dock them again later on. So you can build a network through these standard interconnects on a modular system in space, a modular satellite that's just kind of floating there by itself. If you remove one module, you have to be able to get a connection from point A to point B. Sometimes there has to be another structure around here. You have to be able to reroute. If this is now a free-flying module, then you need wireless in order to talk to it. Maybe it fell off. Maybe you need to talk to it and notify ground control that it's now free-flying. The problem is really everything is dynamic. Everything changes. And you have to be able to handle it autonomously because there's nobody up here to look at the thing and say, you know, there's a change. You know, we have to fix it somehow. The easiest way to do this is by making the protocol simple, explainable, reduce the number of modes of failure. If you ran internet through this, TCP/IP there's lots of ways TCP/IP can fail. Everybody here, put your hand up if you had to sit and wait for a web page to load for several minutes. Yeah, basically, that's why we can't use TCP/IP in space. Basically, because you don't have that kind of overhead to sit and wait for things to figure themselves out. It works just okay on Earth, but we really need a better solution. We have a couple of better solutions. We've developed several modifications of TCP/IP, which runs our internet. And Wang et al. Made a very nice little paper that summarizes all of these, which is a great primer, by the way, to the field of space communications. Most of them, in fact, are either usage of TCP/IP or modifications to TCP/IP. There's relatively few that have been developed specifically as a solution to the space environment. My own thought on this is, there's little practical benefit to using TCP/IP in space, because as soon as you adjust it for time delay and frequent bit errors and things like that, it's not going to be compatible with internet anyway. So in my work, I focused on these last three over here. This is what we are building our solutions for, what we call delay tolerant networking on top of. Delay tolerant networking means basically you have to be able to handle all those delays and errors and things easily without the whole network basically stopping working, like TCP/IP does whenever you get errors. There's something called bundle protocol and an implementation called DTN2. This is actually actively used on spacecraft. It's actually part of what they use for the deep space network and other ways of getting data around in space. It's been around for a couple of decades now. Bundle protocol is a way of putting a bunch of protocols together in a delay tolerant manner. No way that we're going to design one protocol and have it work for everything, right? Engineering doesn't work like that. But we can bundle them together into what they call a bundle node. And then you have a set of bundle protocol agents, each of which handles a certain protocol underneath this. It could be TCP, it could be UDP, it could be something completely different. And you can bundle TCP using a convergence layer protocol, it's called, down here. So it can carry other things, but the point is it carries these other protocols in a tolerant manner. It also uses what's called store and forwarding routing. Store and forward means you keep a buffer at each node of all the protocols that are going through it. And then you have to keep track of when that data package gets sent to the next node. And you have to keep that data around in case the link fails and it never gets to the next node. This is something internet on Earth doesn't do. So it's actually very, very important over these unreliable links. It does mean you need large buffers. So you have to have very efficient buffer management. That's a key thing. There's also something called CFDP, which is the CCSDS file delivery protocol. CCSDS is basically the board that manages the standards that are used for digital systems in space. CFDP is kind of like FTP. It's a file delivery protocol, except it is designed for unreliable links. It's delay tolerant. It can handle delays. It has better throughput performance than FTP and TCP. You can use it on Earth, in fact, and you will find that it's a lot more efficient than FTP in many cases. You can use it either over TCP, if you don't mind unreliable service, or you can use UDP, which is reliable service. If you're running this under bundle protocol, you get that store and forward mechanism, making sure that stuff gets stored and saved until it gets to the next link. It performs quite well, actually. They use it quite often with bundle protocol in space systems. It's the way they upload files to orbit in many cases. Now, there's also something called Licklider Transmission Protocol, or LTP. This is the replacement for TCP, essentially. This is the thing that runs in bundle protocol. It's designed only for single hop links, so your networking has to be added onto this. But LTP is basically a way of sending several streams out of data, and if some of them don't get there, that's fine. The other ones that get there will get there. And it keeps track of the streams that are sent. And it uses an aggregate acknowledgement method to basically say, oh, I only need one response to know which streams got there and which ones didn't. It also runs over store and forward, which means that at each link in your network, it gets stored and then it gets forwarded when the link is available, however long that takes. It's completely delay tolerant. If there is a delay, it doesn't sit there and send retransmission requests like TCP does. It's intelligent enough to back off and wait until the link comes up again. So these are the main tools that are currently used for space networking. What we have to do is now see if we can get them working for us in our space robots, because we don't have that kind of development yet. Oh, one other thing, we've done some work with Craft Prospect as well, and Craft Prospect, which is a company that builds satellite hardware up in Glasgow. Some of you may be familiar with it. They've actually done their own work on routing and fault-tolerant routing. They work on optical links from ground to orbit. They use a machine learning algorithm that actually optimizes the routing of ground to orbit links. The deep temporal regression model, it's called. And they have found that actually using a DTR machine learning model can improve the performance of routing in a network where there's links, when there's link delays, when there's link outages due to cloud cover and other things. Basically, they just pull a short time series of traffic statistics at each node in their network routing. And they can predict the link quality for a given route. And once they predict the link quality, they can actually, they reroute traffic to the links that have the highest quality. And they've actually shown significant improvements using this. They've actually been able to get reasonably good throughput compared to with no intelligent rerouting whatsoever. So this is another tool in our toolkit for being able to do wired and wireless routing really in space. Now over to the modular side. With respect to modular robots, we don't really have a precursor in space. We have lots of modular robots we've tried out here on Earth. Needless to say, they do not satisfy any of those criteria that I've already talked about. But looking at modular robots, you know, we've looked at them for a while. There's a couple of situations like Modular and iBoss that I mentioned up here, where we start to consider modular satellites in orbit. The communication problem has not been solved yet, though. Looking at the kind of technologies they use, I mean, they use pin and latch connectors, bolted connectors, keys connectors, hook connectors. They use similar technologies to the kind of stuff that we're adapting on orbit. What you don't, you even see things like genderless connectors. You see electropermanent magnets holding things together, for example. You see solder for solder cubes, friction pin fits. What you don't see is the kind of environmental tolerances that are necessary to make things work on space. So using this as a basis is, you know, what we've done in Mozar and other projects to develop standard interconnects. Modular robots traditionally have used magnetic connections, hook connections, keyed connections, bolted connections, and so on, because they're simplest, because they're easiest and they work the best. In terms of communication protocols, infrared and simple serial, and sometimes CAN bus have dominated because they're easy to use. There's a good overlap here actually in some ways, because keyed and bolted connectors are used in space quite a lot. CAN bus is also used in space hardware occasionally. So there are, you know, some touching on these things. There's also some wireless communications, but as mentioned, that hasn't been done in space. And things are more or less the same over time. I mean, if you look at the way modular robots have evolved, you can still see that simple RS-232 serial is dominating. It's the easiest thing to use because every microcontroller uses it. More recently, you start seeing CAN bus, BLE, and Wi-Fi. What you don't see is that dynamic robustness to changes, the ability to continue communicating under dynamic changes that have been autonomously accomplished. Most of the time you have people overseeing these things, and that's the aspect that we want to improve on. So about that system that we've developed, this is basically it. Some of you might have seen these slides before. We came up with a name for our modular system that we developed at York. We called it MoStar. This specifically is called MoCube, although we could theoretically have other shapes. And the idea behind MoCube is that you have a module that has 6 sides. Each one of these sides is called a tile. Each tile can have different stuff on it. We can have NVIDIA Jetsons, we can have Xilinx Zinc modules, we can have Raspberry Pis, batteries, motorized joints. All of these things we can put together into a module, and each side of the module has something different on it. It's like a way of building cells in the human body, where every different kind of cell has a different function, has slightly different contents. So this is what we've been using to experiment with and explore the range of things you can do with modular robots so far. And so we split this up for purposes of control within a single tile, and said, okay, there's going to be a nucleus of a cell, right? There's going to be a nucleus of a tile. We call that the master board inside the tile. It's kind of responsible for managing the rest of them. And then we have slave tiles here. The slave tiles are simpler, cheaper, don't have as much stuff on them. They can basically communicate with the master. They have a connector on the outside to communicate with other tiles, and they have another task, say. And the motors here drive the connection mechanism that we use, that was developed by a PhD student of mine, James White, in his PhD. He graduated at the end of last year. I'm happy to say he's actually he's in a company called Forlinx now, building low-cost space wire hardware. Doing quite well, I think. And one of the innovations he came up with is this idea of having rotating magnet pairs to hold these tiles together. And they're actuated by these gears here. Behind these rotating magnets, you have pogo pins. These pogo pins contact the magnets, and you can actually send power and data through the magnets. So this is our connector design. MoCube standard interfaces, they're called. So James White developed this rotating pairs of magnets system. It's advantageous because it's androgynous. Any two can connect together. It has single-sided disconnect because only one side has to rotate the magnets, push itself off. It's flat surface with electrical protection. So if you put it on a conductive surface, it's not going to destroy anything. It has 90-degree symmetry. You need multiple symmetry angles if you want to have lattices, like a cubic lattice. And we have 4 separate electrical contacts, which is enough for Ethernet, repeated twice on this system. We can make them active or fixed or passive, and you might also be able to connect. I did in my original design, I had an infrared transceiver in the center there, so it actually has wireless as well. Again, infrared, very popular in modular systems. No thermal or fluid transfer yet. We'll deal with that when it goes to space. The active connector design is really based on this idea that if you line up magnets, you can either make them attract if they're opposite polarity, or you can make them repel. You can actively disconnect, which means you can repel them, or you can rotate the magnets by 90 degrees, and the magnets will basically not interact. So it's like switching off the latch. It works quite nicely, actually. It works quite nicely because it's a relatively simple single degree of freedom way of latching and unlatching, and it pulls itself together because they're magnets. Mechanical characteristics, you might think magnets are actually not that great, but we did manage to get almost a kilogram of twisting load and over a kilogram of bending load off of these. Axial load, if you try to pull them straight apart, it can handle 2.5 kilograms. Each one of these modules is less than a kilogram usually in weight. So these are actually fairly reasonable numbers. A lattice can hold itself together against the force of gravity, which is really what we were aiming at. And we chose as our communications protocol, Ethernet. Why did we choose Ethernet when most of the other module systems that I showed you before, with the exception of one, do not use Ethernet? Well, Ethernet's more complicated, yes, but it has many of the things we need for space systems networking. It has that ability to, to electrically decouple because it uses transformers, so it won't short. It's very high bandwidth. It's relatively few wires. 100 megabit Ethernet's only 4 wires, so that fits on our connector. And it is cross-compatible with EtherCAT, time-triggered Ethernet, and all the other variants on Ethernet. So cross-compatibility is really nice. We got all that wonderful hardware available. So what James did is he implemented a 100 megabit router for 4-wire Ethernet links using his own protocol that looks towards all those requirements that we talked about for space networking. And basically we are caching, again, using a store and forward model, we're caching data on each node using this router. And we're saving, the most recent packets that arrived, the metadata associated with that, what the packet is, where it's going, when it arrives. We also have to cache a network routing table. The routing table basically says where I have to send it next, what module you have to send it to next, or which side of this cube you're sending the data out next in order to get to the next hop in the network. And so each router basically handles six sides of a tile. So there's 5 connectors on here plus the master tile connector, which is on the other side of this tile here. We did come to a very good review about Ethernet. We reviewed SPI, I2C, CAN, LIN, UART, FireWire, SpaceWire. Some of these are too expensive, like SpaceWire, too hard to get. Some of them don't have sufficient bandwidth, like I2C, CAN bus. There's a lot of reasons to use Ethernet. As I mentioned, it's a very easy decision to make for robotics based on the evidence. And when you come to Ethernet, you always hear about the OSI stack developed a long time ago as part of the methodology for how we are going to create an internet. The OSI model was actually not created specifically for TCP/IP. They created their own protocol, and TCP/IP took over because it was better in most people's eyes. But the OSI stack remained, and it's 7 layers deep. This is all software. The more layers you have in a software system, as you're probably aware, the more modes of failure there are. A lot of my work has been focused on trying to get rid of some of that complexity and get something down to the very simplest it needs to be so that the software can work, do its job with the minimum number of failure modes, and be validatable, verifiable for things like StarFab, where software has to work and has to be verifiable. So we tried to reduce this down to 4 layers. So instead of 7 layers, most are using a 4-layer model, where essentially it's distributed horizontally. This is what we call wide computing. We have applications, which is what you write. Variables, these are essentially your state variables for whatever node you're writing, whatever system you're on. They have to be cached, they have to be monitored because of that store and forward mentality. You have to cache on each node what each node knows and what needs to be sent in and out. You then have the transport layer, which is basically the protocol. And then you have the hardware down here, which is Ethernet physical layer, the MAC, the physical interface, and the RMI interface. We do something else. Lest you think that we're all about Ethernet now, we do actually use a CAN bus within the modules. The reason we use a CAN bus within the modules is we need a secondary layer to handle this management, basically. If the Ethernet goes down, if there's a problem with routing, or if you have a module tile that's a tiny little microcontroller that runs a motor and doesn't need Ethernet, would be a waste of effort and resources. We use CAN bus internally in the modules. CAN is great because it's a 2-wire bus. You can talk to all of the tiles, all 6 nodes on the same 2 wires. Very convenient. Downside is if you connect it externally, as soon as you short these 2 wires together by putting it on a connected surface or something, the whole bus goes down. So we don't have any external connectors. It's only internal. All the externals are Ethernet. Now, there's another great advantage to these connectors. First of all, if you take 2 connectors and you put them face to face, you know they're mirror images of each other. With Ethernet, and as any serial protocol, you have a transmitter and a receiver. Usually TX goes with RX, right? And RX goes to TX. Well, rotating them around, putting them face to face actually does that. We've distributed the receiver and transmitter pins around 8 magnets, such that if you put them together face by face, RX goes to TX, TX goes to RX. It's a crossover, which they call MDIX in Ethernet speak. Then you have this problem. What happens if you rotate the module? Well, if you rotate the module 9 degrees or 270 degrees, what that does is it crosses over the pairs. It actually causes your pluses to go to minus and your minus goes to plus on a differential bus. Usually that's a problem. Fortunately, modern Ethernet physical layers can handle that. They can even detect it. So we can actually detect what angle it's at, and we can compensate for that using the physical layer chip on Ethernet. Another good reason to use Ethernet is it can actually handle swizzling of the wires together, which is something that most protocols can't. So the Mo protocol, MoStar, as I mentioned, is simpler than Ethernet. If you were to compare it, Ethernet starts with basically preamble, and then it has destination MAC, source at MAC, length, data information, data, and so on. This is your basic 802.3 data frame coming out of the Army interface. We've simplified that down. We have basically a module ID. So module ID in the system, source, destination module, source module, what kind of data it is, the length of the data, and then 2 checksum bytes and data after that. It's a simplified system. Granted, right now we can only handle 256 module IDs, but this is expandable. We're experimenting with it to see if this works first. And if this works well, we can probably expand it. We could make an IPv6 address and use a few more bytes for it. But that's the way it is right now. Frame transmission and reception is basically a state machine. This is built off of the reduced media independent interface, the Army-based frame system that is used in pretty much all Ethernet interfaces. Suffice to say, it's simple and it's effective, I suppose. And we've built, in order to verify that this actually works, we've built a network simulator. The network simulator that James White put together is one of those rare examples of a cyber physical simulator. I think maybe actually RoboStar might be actually the other example of a cyber physical simulation system that actually is sufficiently comprehensive to do this kind of thing. But what he did is he put together a Unity simulation with a Ethernet simulator based somewhat on NS3, which is a standard intranet simulation engine. We didn't use NS3, and the reason was because changing NS3 to handle the protocol that we developed was too much trouble. So he just wrote his own simulator. And it communicates with the Unity simulation engine using sockets. So we actually have the ability to develop a configuration of modules like this and then simulate the movement of packets through the system. And we have done a little bit of testing. The tricky thing with James's PhD is, like many students, he spent so much time building the simulator, he didn't really have a lot of time to do testing with it. So further testing is pending. However, he did manage to test dynamic changes of configuration in a 27 module system like this, where you can move modules around and you can see the changes in latency, you can see the changes in time taken for routing and the changes in the routing tables. And it does go up if you add more modules to the system. The amount of time it takes in microseconds to transit does go up as well. It's very consistent though. It gives you a very predictable pattern of exactly how long it takes to get somewhere in a modular system of a certain type. And that's what we want. We want it to be predictable. We want it to be repeatable. It's difficult to compare timing to TCP/IP in this case because they're very different systems, completely different routing. But we can show that this system is a little bit more robust in terms of if you change things around, it will reroute, it will reconfigure actually, and you'll be able to get your packet from point A to point B just about as easily as you did originally. You don't have to change addresses or anything. So it's way better than TCP/IP in terms of handling change. So we still have to work on scaling the protocol, doing some more simulation, being able to make this work in the cyber physical system. We need to build more modules. That's another thing that we're behind on. Now, having done this, the new frontier, as I mentioned, is wireless. This is the nascent part. This is the part that is largely unexplored. And we're just starting on this, really. There's a little bit of work in small satellite constellation networking using wireless. There's a little bit of work in proximity operations like docking. But there's not a lot of exploration into how this is actually going to work for short distances, for lands, essentially, in orbit. What the most appropriate topology, rather than Ethernet, which is kind of a star topology of networks, the most appropriate in this case is actually a wireless mesh. You've probably seen wireless mesh advertised as part of, Zigbee or Bluetooth or that kind of thing. Mesh means anything can talk to anything else, but it also means that packets have to get routed through other nodes because you can't necessarily have every wireless node in range of every other wireless node. So it's a very tricky routing methodology. Our aim is a little bit more ambitious. We want to try to use as much as possible the same kind of protocol that we use with the wired networking, with the wireless as well. Because that means essentially we can transition from internal connected networks, wired networks, out to wireless with a minimum of overhead, minimum of translation. That's something. It's the same kind of thing they try to do with wireless Ethernet, except of course we don't really have the option of TCP/IP as mentioned. So, we're innovating on this. There's lots of hardware available, although I wish there was more, honestly. As I mentioned, 802.11s, which is the Wi-Fi mesh protocol, Wi-Fi mesh implementation standard, it's pretty closely tied to TCP/IP. And it's very complex. So we're kind of moving away from that. So we've looked at Bluetooth low energy, Zigbee, NB-IoT, which is a protocol that's used in the 5G suite of technologies. Bluetooth and BLE is nice because everybody supports it. However, it's focused on very tightly coupled descriptors to the things that are being transmitted. We want to transmit arbitrary information. We want to bundle them effectively, like bundle protocol does. So we can't really fit it into the restrictions. Zigbee is great because it's serial transmission, but it usually requires a coordinator for provisioning. Provisioning is the process of adding new nodes to the system, setting them up with an address, setting them up with routes, and so on. We want to try to make it a true mesh. NB-IoT largely does that, in fact. It's a very promising technology. But it's very hard to get hardware for it. We can't really test on it. So the only thing we could do is kind of implement with software radios. We've had some chats with the communications group about how we're going to do that. There's a few proprietary mesh networks. We can't really hack them. We can't really modify them. So we haven't been able to do much with those. And we could always just get some software radios and build our own. We'd love to, but it would take a lot of time and work. So we haven't gotten to that point yet. So there's really no ideal system. There's no perfect fit to how we can take what we've done with Mostar and adapt it into wireless. However, based on previous experiments with wireless in space, we are trying to move things mostly into software and not relying on the hardware stack like Bluetooth does, because it makes it more portable, because you can put it on anything then. So it's mainly a software implementation. We're using ESP32C6 modules right now. We're connecting them largely as a Zigbee network, as close to a mesh as we can get with Zigbee, to be able to send most our packets around to different nodes. And that's the state where we are right now. So I can't say that we've actually we've got too many fancy results to show you as of yet. Hopefully, in the context of StarFab, hopefully we'll be able to do some more experiments. Now, there's one more thing, one more hiccup that I have to talk about, which is serialization. You've got all this wonderful data. All your robots have to talk to each other. If anyone here has ever used, things like 0MQ, or if you've used protocol buffers or ROS even, you're probably familiar with the problem of trying to get robots to understand each other's dialects. We have a wish list for the storage of our data, for the data that we're sending over our MOSTAR protocol. We want it to be schema-free, no style sheets and limitations on what variables we can send. In the future, we'll be sending up modules that have fancy new sensors. Maybe we'll have a Play-Doh sensor or something like that, and we need to send Play-Doh packets over the network that we've never seen before. We have to be able to route those. We can't rely on what was there when we sent the spacecraft up. We need to have dynamic size, because sometimes we're sending point clouds, sometimes we're sending individual bytes to motors. Dynamic types, data plus semantics, binaries, programs, we want to send it all. The semantics have to be consistent system-wide for reasoning and autonomy. There's also a thing called zero copy. When we did some of these space projects previously, we used ASN1. Maybe some people are familiar with ASN1. Very old compiled in protocol for communications, for sending messages around the robotic system. ASN1 is so inefficient that it took more time to convert data from the internal memory format into the format that was being sent over the communications link than it did to process the sensor data in the node. Most of our overhead was just copying them. So we want to try to achieve zero copy, which basically says data is read and read in the same format that it's stored. We want it to be efficient in binary, no extensive XML, which is very space inefficient. We want it to be explainable, so we can actually convert it to human readable language. It's a pretty tight list, I admit. Yes, we're being very, very specific about this. We don't have an ideal serialization option, but we are getting fairly close. And we want to be able to find an ideal serialization format, because that increases the reliability and increases the efficiency of the systems we build, decreases the number of failure modes, decreases the size of the programs, all of these things. So if you want to compare all of the popular serialization formats, I'm not going to go over this in detail. Those of you who've actually tried to send data over network links might be familiar with some of this. ASN1 is probably my least favorite because of my experience with it. XML and YAML are used everywhere, but they're horribly inefficient as soon as you try to send them over a communications link. The best ones right now, Captain Proto, which was developed by the guy who developed Google's protocol buffers, once he discovered how it should really work. It's actually zero copy, it's very efficient. Flat buffers, which is what Google did after the guy who developed Captain Proto developed it, because they realized what they should have done. And DOL, which is kind of a strange language for converting one format into another efficiently. We're hoping that through further examination, we will find a good solution. So all the robots in the future can talk with each other and actually understand each other for years, for decades, because that's how long these satellites last. So looking back a little bit, we started with bundle protocols, which is what's used for sending stuff, heterogeneous stuff over over network links in space. And we're trying to sort of synchronize the system that we've developed for MOSTAR with it. And there are similarities. I would say the thing about bundle protocol is it's got several layers. It's got a lot of complexity, but you can put pretty much anything in it. You can bundle any protocol in it, send it over any network links, and it should be understood. So it's good that way. Our system is much simpler, but it's focused on robots. It's focused on intelligent systems. So we focus on, first of all, efficient nanokernels, no complicated systems, preferably not Linux, as simple an interface to hardware as you can possibly get. The MoStar protocol, which is our link layer here. Semantic variables. These are, if you know my other work in probabilistic systems, we try to send random variables so that we can do probabilistic inference. And then our applications, which by the way, are isolated and containerized, because in space systems, you don't want to have seg faults. So everything is carefully containerized in these kind of software systems. And so this is what we have right now. And I hope this has been an interesting trip through the challenges of space networking for you. We have, in summary, I would say we have found most of the basic tools we need in order to solve the kind of networking problems we have in space. We know what the problems are, and we know what we need to do next. However, we're not very close to having a complete solution because we can't just port TCP/IP and everything and other things over. We can bundle them together. We can heterogenize all of our space networking systems, but that all increases complexity and it increases the difficulty of making it all work together. And we're trying to make that simpler and easier. So we're not quite at the point where I'd like to be there. We've got some terrestrial hardware and software. As I mentioned, wireless, lots of options. None of them are ideal. Need fundamental improvements. Once we make these improvements, once we crack these problems and get these modular systems talking to each other dynamically, handling all of these challenges, we'll have very robust terrestrial robots. Imagine a ROS, except without all of those connection problems you always have when you're running it over Wi-Fi, We want to be able to solve these problems, and we want to be able to bring them back to terrestrial robotics. And the MoStar system we've developed is really the platform on which we are now building this work, and we're trying to robustify modular robotic systems. Thank you very much, everybody. So I'm happy to take any questions or criticisms. Yes?
Thank you very much for the presentation. As usual, very entertaining and interesting. Thank you. Being in this building, and I'm sorry I missed the beginning, so I may be asking things that you already answered. I think of three concerns.